Hello, friends. Thank you for being here. We're going to start on a new chapter, Chapter 9, Polar Coordinates and Vectors. Very interesting, useful chapter, one of my favorites. And in this chapter, we're going to take on 5 sections. This lecture, of course, is going to cover section 9.1, Polar Coordinates. So let's begin with polar coordinates. Polar coordinates are very useful alternative to Cartesian coordinate system or rectangular coordinate system, which is the only coordinate system that we have talked about in this course so far. Remember, for the Cartesian coordinate system, it's made up of the x-axis and the y-axis, right? So we got the axes, and then every point has a unique representation, right? So for example, this is point 3,1, very basic. The origin of the coordinate system, of course, is at 0, 0. So we basically have two number lines that are orthogonal or perpendicular to each other. Now, with polar coordinates, what's interesting is that we have just a ray, which is like a half line. You see that? All we have is a ray, and that's all a polar coordinate system has. There you go. That's it. Isn't that cool? And by the way, there's literally a dozen, if not more, 12 or 13, last I counted, different coordinate systems in mathematics. So this is one of them we're talking about, polars. By the time we get through, therefore, you know about 2 out of many coordinate systems. In your calculus courses, you also learn about cylindrical coordinate system and spherical coordinate system. So by the time you get through your calculus series, you're aware of 4 of about 13 total coordinate systems. So there you have it. This is what we call the polar axis. That's what that is. So how do we have a point represented on a plane, for instance? So let me make something up here. Suppose this is my point on a plane, point P. So every point on a plane, no matter where they are, could be represented by the means of a distance from the pole, which is the initiating point of the polar axis. So this is where the pole is. Okay. So it's going to be represented, the point P here has a representation by means of a distance from the pole, which we use R for that, okay, and the measure of an angle theta. So every point is represented by means of R comma theta. And again, just like with the Cartesian or rectangular coordinate system, every ordered pair has coordinates x, y. The order matters when we write these coordinates. So in polar coordinates, we always write r, the radial distance, if you will, from the pole to the point first, followed by the measure of the angle. If the angle goes in a counterclockwise direction, then it's assumed to be positive, and the angle, if it goes in a clockwise direction, then it's going to be a negative angle. Okay, and that's really all that is. So for example, just to show you a few examples, so let's say here's my polar axis. Okay, and then maybe I use a red for that. And there you go. And this would be like the x-axis kind of. There's the polar axis. Oh, the pole, by the way, the pole has coordinates r0, theta 0. And it's coincidental that the origin of the rectangular coordinate system is also 0, 0. So that's kind of interesting. So it has coordinates 0, 0. And suppose I have now a point here, for instance, that sits at an angle of about, let's make that 40 degrees. And the radial distance, let's make that 5. Okay, so this point has coordinates 5, comma, and in degrees, it would be 40 degrees. And of course, we can write this in radians, but I'm going to stay with degrees because the measure of the angles, I don't want them to be special angles, so I have to use pi's. Could be anything, could be 27.7 degrees, whatever. So here we have the representation of that point. Now, if you note here, by the way, if I take a this is in a counterclockwise direction right now, but if I choose a clockwise direction to that point, I can also get to the point if I travel in a clockwise direction, correct? Now, in a clockwise direction, I would go, 320 degrees, so the total is going to be 360, right, to complete the circle or rotation. Therefore, I can write the same point using 5 comma negative 320 degrees, because remember, if the rotation in a clockwise direction, the measure of the angle is assumed to be negative. Okay, so there you have that one. And that's not the only way I can write the representation of the point. Consider subsequent rotations around the circle. Each 2 pi will generate a circle here, right? So for example, I can go one rotation, I can go another rotation. So multiple rotations will also be correct as coordinates of a point. So if I go, for example, at 360 to 40 degrees, I'm going to get 400 degrees. And there you go. That's also the representation of the point. If you go in a negative direction, negative 320, add another negative 360. So that's going to be negative 680 degrees. And there you go. You have another representation. 5 and negative, I said 680 degrees. So you kind of see here what's going on with this. The polar coordinates of a point are not unique in polar coordinate system, whereas in a Cartesian coordinate system they are unique. So how are we going to get around this? Well, there's going to be some kind of a convention, right? So let's agree that we're going to make R positive, okay? And we're going to choose theta to be positive also. That would be the convention that we're going to use. And usually we go from 0 to 360 degrees, okay? Typically, theta lies between 0 and 360 degrees, okay? So this way we all get the same coordinates. Otherwise, I mean, imagine if everybody wrote their own coordinates and they're all correct. Well, that's going to make it a little confusing, right? Now, also, the fact that I wrote we agree R to be positive here suggests that, well, can R be negative? And the answer is yes. So let's take a look at the case where R is negative and how that's handled. So here's my polar axis. Okay, and suppose this point here is going to be 5 and 40 degrees, the one that I just showed you up here, the only example I have so far. So suppose that's that point. If I want to plot the point negative 5 and 40 degrees, see, notice now R is negative. So what we do is actually reflect this point 180 degrees. So if you reflected 180 degrees, this is the point negative 5 and 40 degrees. There you have it. So that is how we handle negative values for R. Okay. Now, this point itself, the negative 5, 40, if you go in a clockwise direction, let's see, this angle is 40 degrees, and that means this angle is 40 degrees. So the supplementary angle to that is going to be 140 degrees, except if I go in a clockwise direction, it's going to be a negative 140 degrees, correct? The measure of the angle. And therefore, so that makes it to be 180 again. 140 and 40 makes 180. So I can actually write representation of this point, negative 540, as 5, a positive 5, and negative 140 degrees. Right? That would be exactly the same point. All right. Now, the point that I started with 540. If I need to write this point using a negative r, this is how it's going to work. If I think of the point now as positive 5 and measure of angle negative 140 and reflected 180 degrees across, okay, so I'm going from here and reflected across. Okay, so what am I going to get here is going to be the point negative 5 and negative 140 degrees. Isn't that cool? So you can kind of see again how many different ways we can represent the coordinates of a point in polar. So let's generalize this then, based on what we have observed. If r theta are coordinates of a point in polar coordinate system, then every point with the same r and theta plus 2k pi, that's subsequent rotations around the circle, right? That gets you to the same point. It's going to be also a coordinate. And if you want to have a negative angle, then a negative radial distance r, you can use negative r and then use theta plus pi for the measure of the angle, and then of course plus 2k pi for subsequent rotations around the circle. So we can do that. This would be the general representation, and notice this is an infinite set, right? And by the way, k, as always, I've mentioned that before, k in all our notations, k has been an integer. Okay, that's what k is. K is an integer. And remember what integers are, right? Like -3, -2, -1, 0, 1, 2, and so forth. So that's what k is. So there you have all infinite representations of a point. Okay. And there it is, polar coordinates. Very simple, very useful. As we proceed through the chapter, you see the usefulness of this coordinate system. Now, how do I convert from polar, let's say, converting from polar to familiar rectangular coordinate system? Instead of question mark, let's just make it as a title. So let's say we want to convert from polar to rectangular. To do this, we're going to kind of superimpose or overlay one coordinate system on top of the other. So here's our familiar Cartesian coordinate, and then this would be the polar. Polar is pretty easy to do, right? You just draw that half line, the ray emanating from the point O here. So here's the, again, overlay of the two coordinate system. Now, if I choose an arbitrary point, now usually we choose the point in the first quadrant, but they don't have to be. It could be here, 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 doesn't matter. Because we use general variables, so the signs will adjust themselves miraculously. Okay, so if in terms of coordinate system, well, let's look at rectangular. In rectangular coordinate system, this point has coordinate x and y, correct? So the point has representation x comma y. All right, and this is going to be exactly the same point. So we're going to call it r theta. And what is r? R would be, it's like, again, the radial distance, they called it, the direct distance from the pole, from the origin to the point, and we're going to choose theta to be a positive angle. Okay, so this would be the connection between the polar and rectangular coordinate system. Now, the specifics of it. We want to go from polar to rectangular, right? Okay, so for polar, that means you're given r theta, you want to find x and y. So how are we going to do this? Well, if you think in terms of a right triangle here that I have, right, which right I'm thinking about O, call it P, and then right in here we have this right triangle. We can use Pythagorean and say r squared is x squared plus y squared, right? So this would be the relationship between between the rectangular and Cartesian coordinates. R squared is x squared plus y squared. Now, what else? Let's say we have polar to rectangular, right? Okay, so the measure of the angle here, if you think about now the trig function, for example, cosine theta. Well, cosine theta is adjacent over the hypotenuse, right? So it's x over r. So from this, we get x is equal to r cosine theta. There you go. Remember, we're going from polar to rectangular, means you're given the polar coordinates. I'll do an example in just a moment. So given r and theta, this is how you find x. Well, how are we going to find y? Well, if I go sine theta is the ratio of opposite in a triangle, right triangle, opposite to hypotenuse. So it's going to be y over r. And from this, we get y is equal to r sine theta. True? And there we have it. So we convert. This is how we find x and y. And really, that's all we need, right? Because in rectangular, we only have x and y. Now, how do we convert the other way around? Let's say we want to go converting from, this time, from a rectangular to polar. So in other words, you're given the xy and you want to find r theta. Well, we already mentioned r squared is x squared plus y squared. Remember, the given are the coordinates in Cartesian. So those are given, therefore we can find r this way. And we take the square root of r squared, of course, and the positive root is going to be r. How do we find the measure of the angle? Well, again, in this triangle, if I look at tangent of theta, that's very common to use tangent. You could use cotan, but usually we use tangent. That's the ratio of y to x. Remember, we're given x and y in rectangular. So if I form the ratio of y to x, which is tangent, from this, I can solve for theta, right? By definition of inverse, theta is going to be the arctan of y over x. And there you have it. Now, this will assume that theta, remember the range of inverse tangent is from negative pi over 2 to pi over 2. That's just to make the function 1 to 1, correct? All right, and if the measure of theta is, in other words, theta between negative pi over 2 and pi over 2, that means theta is in the first quadrant, or theta is in the fourth quadrant, right? Remember the circle that I had earlier? There you go. This is first quadrant, fourth quadrant. That's negative pi over 2, and that's pi over 2. Then, well, what if what if the angle, or what if the point is in the second or the third quadrant? Well, then we need to make adjustment to theta. In this case, theta is going to be pi. We need to add pi to it. Okay, it's going to be pi plus the arctan of y over x. And that way we have, the point will be reflected. If it's in the fourth quadrant, it will be reflected in the second quadrant. If it's in the first quadrant, it will be reflected in the third quadrant. Okay, and then for this relationship I have, let me put it right directly below it. Theta belongs to Q2, or in this case, Q3. And that covers all four quadrants. So again, if theta lies between negative pi over 2, pi over 2, make no adjustments. Otherwise, we do need to make adjustments to get the correct coordinates. All right, that's all there is in this section. Again, very straightforward. We have these key relationships to go from polar to rectangular and go from rectangular to polar. So here's R arrow P, rectangular to polar, and I'm going to go P arrow R. That means polar to rectangular. Cool. Let's take a look at Just a few examples here. So in my first example, let's say I want to go from polar to rectangular. In other words, I'm given r and theta. I want to find xy, right? And the point, call it q in this case. I don't know. Yeah, whatever. P, Q, R, doesn't matter. Point q, call it. It's at -2, and suppose it's 3 pi over 4. So let's plot this point first of all. And here's my polar axis. Now to do -2, remember r is negative here. To do negative r values, radial distances, we actually plot the positive r. So I'm going to do 2 and 3 pi over 4. And then we do a reflection to adjust for negative r. 2 and 3 pi over 4. So 3 pi over 4 is going to be the measure of the angle here, right? And there you go. That's 3 pi over 4. And 2 is the radial distance. So this is the point. That's 2 and 3 pi over 4. Right? It's that point. The -2 therefore reflects it across right in here. That's going to be -2 and 3 pi over 4. You don't adjust for the angle. Okay, when you reflect, you just adjust for r. And there you have it. And this is the final answer. Okay, and of course we have polar. I'm going to have the coordinate system, just like we have rectangular coordinate systems. We have polar coordinate systems. We can actually have the I'll do one here where I don't have to do it by hand. I actually just copy the coordinate system, so it'll be more accurate when I plot these points after this one. Okay, so this is again, this is the point, right? This is the point that we're looking at. So from this, it looks like the XY coordinate system, if I throw that on top of this, the XY coordinate system suggests the point is going to be in the fourth quadrant. It's going to have a positive x, negative y, right? Let's see how that's going to work out. Remember, x is r cosine theta. And r, the radial distance, r is -2. And we go cosine of 3 pi over 4. And this is going to be cosine of 3 pi over 4. That's one of the special angles, right? If this angle is 3 pi over 4, here this angle is pi over 4, correct? The reference angle is pi over 4, and cosine of pi over 4 is √2 over 2. And it's going to be negative, right? Because we are in the second quadrant, cosine negative. Second, third quadrant, cosine is negative, so it's negative √2 over 2. And the double negative makes this just square root of 2. So the x component is square root of 2, which makes sense because the point is in the fourth quadrant. I would expect y to be negative. Let's go r sine theta. R sine theta, and this time again r, we're going to keep it as negative. Whatever it is, don't change it to a positive. R was given to be negative. And sine theta, that is sine of 3 pi over 4. And in the second quadrant, sine is positive, so it's -2 times √2 over 2. And that's going to be just negative square root of 2. So we see how y turned out to be negative. And again, it makes sense because I'm in the fourth quadrant. Here's the point, and the answer is √2 comma -√2. Okay, now let me bring my clean, nice coordinate system, and I'll do the same thing I plotted on the nice coordinate system. Okay, so here I have my clean coordinate system, nice and much better than the one I do by hand. Okay, so the point, again, let's plot the point 2 and 3 pi over 4. Now here, we notice that this the grid here, the polar grid, is made up of concentric circles, right? That means concentric meaning they have the same center, different radii. So a circle of radius 2, this is a circle of radius 2 right in here. You see that? That's radius 2, 3, 4, 5, 6, and so on. All right, so the radius is 2, the angle is 3 pi over 4, and of course 3 pi over 4, that's going to be 3 times 45 degrees, which is 135 degrees. And that would be right about here. There you go. See that? That's 0.2 and 3 pi over 4. So negative 2 3 pi over 4 is when you reflect that across. So it's going to be right in here. And there it is. That's going to be the point. This is negative 2 and 3 pi over 4. And that's exactly what square root of 2 and the negative square root of 2 are going to be. There we go. Square root of 2 is about 1.4. And there it is. This is negative square root of 2. Negative root 2 is here, and that's root 2 with respect to the xy coordinate system. And there you have that one. Okay. Well, let's do another example. Suppose we just want to plot the point here again, and we're going again from polar to rectangular just to do a couple of examples. This time point Q, let's say this one is negative 5 and negative pi over 6. Okay, now remember pi over 6 is 30 degrees. So let's do our x. X is r cosine theta, so that's going to be negative 5 cosine of negative pi over 6. And remember the negative angle identity, cosine of negative theta is the same as cosine theta. So that's 5 cosine pi over 6. And cosine of 30 degrees is root 3 over 2. Correct? So that's negative 5 times root 3 divided by 2. So the whole thing is negative 5 root 3 over 2. X is negative. And let's do y. Y is r sine theta. And r is negative 5. This time I have sine of negative pi over 6. The sine of a negative angle is going to be negative sine of the angle, of a positive angle. Pi over 6. See the negative here? Offsets the negative in here. Okay. And double negative makes positive, so that's simply 5 times sine of 30 degrees, which is 1/2. So that's 5/2. Remember, these are a special angle, so we should know their exact values by now. And the coordinates, the xy coordinates of the point, are going to be negative 5 root 3 over 2 and 5/2. Okay. Now, if I again plot this point, let me, there you go. I'm going to bring my coordinate system and try to plot the point here for you. The point is, let me copy it here. Cool. So we have, again, negative 5 and negative pi over 6. Pi over 6 again is 30 degrees, right? So I'm going to go 5 and a positive 5 and a negative angle. Negative angle means clockwise direction, and the radial distance is 5. So I'm going to be on a circle of radius 5 this time. That's this circle right here, right? Circle of radius 5. Negative 30 degrees, so this is roughly negative 30 degrees is about here. And let's call that 30 degrees. So here's going to be, that's where the point is. You see that? The measure of angle here is negative 30 degrees, negative pi over 6. Now, the point that we are seeking is negative 5, right? It's negative 5. So how would I plot that point? Remember, we're going to reflect across. And there you go. You're going to reflect this 180 degrees. And when we do, this is going to be the point right in here. This is going to be point Q. And you can see that in terms, if I superimpose the coordinate system, the xy on top of this, you'll see the point is in the second quadrant, x negative, y positive. And there you have it. Okay. And there, we just wanted again to plot this point. Now, this time let's go from rectangular to polar. Okay, the first two examples were polar to rectangular. Now you'll be given x and y, and let's say we want to find r theta. So the point Q has, let me just remind, this is xy. Q is given by 1, -1. Okay, we are in Cartesian. We want to convert to polar. Okay, so let's do that. Remember, in polar, I need an r and a theta. So r squared is x squared, y squared. So you square each of the Cartesian components. 1 squared plus -1 squared. 1 plus 1 is 2. Now that's r squared. R will be square root of 2. And remember, we take the positive root because we agreed r will be positive. So r is going to be root 2. And theta, the theta is going to be arctangent of y over x, provided we are between -90 to 90 degrees. Otherwise, if it's not, then we go to we add pi to it. Now let me also actually graph this without my fancy grid, just by hand. So this is my polar axis. The point, let's see, RP. Okay, and the Cartesian, there we go. Let me say this is x and there is y. All right. Now the point is 1, 1. So let's say here's 1, there's 1. And this is what Q is, right? That's point Q. So we need to find R, and this is what we just found. We found that to be square root of 2. The measure of angle theta. It's because Q is in first quadrant, that point is in the first quadrant, so I don't need to adjust for the arctangent. Okay, so this is going to be arctan of y -1 over 1. And this is arctangent of -1. Now arctan of -1, the measure of the angle is going to be, oh, hold on, so sorry, it's 1 -1. What was I thinking? See, I'm sure you caught that. Y is -1. This is actually where the point is in the fourth quadrant. This is Q. R doesn't change, right? R is positive. We take R to be positive. So that's root 2. But the measure of the angle actually is going to be negative. True? That measure is going to be negative. This is going to be a negative angle. Now arctan of -1, the tangent of 45 degrees is 1. Because it's -1, within the range of inverse, theta is going to be negative pi over 4. Because remember, again, arctangent, the measure of theta will be between negative pi over 2 and pi over 2. And there we have it. Theta is negative pi over 2. Therefore, the coordinates of this point as r theta is going to be, r is root 2 and theta is going to be negative pi over 4. Okay. Well, let's take a look at another example. This next example, again, we're going to convert from rectangular to polar. So this time the point, let's say this point is 5 and 5 root 3. And this is going to be my x and y. So let's do our r squared right away. R squared is going to be x squared plus y squared. X is 5 squared plus 5 root 3 squared. And the whole thing is going to be 25 plus 25 times 3 is 75. So that makes it 100. R is going to be square root of that, which is 10, positive root. There. And for theta, I need to plot the point because before I do theta, I'm plotting the point in the Cartesian. Okay, because I need to know remember, if the point falls in the second or third quadrant, we gotta add pi to the answer we get from the arctangent. Now 5 root 3, that's gonna be, let's say this is 5 root 3, so the point is actually in the first quadrant. Okay, therefore when I go theta as arctangent of y over x, I don't need to add pi to it. And this is going to be the arctangent of y, which is 5 root 3 divided by 5. And that's simply arctangent of square root of 3. Okay, and in the first quadrant, again, we know that tangent of 60 degrees, correct? So theta is going to be pi over 3. Tangent of 60 degrees is square root of 3. Therefore, Q has coordinates r theta. R is going to be 10. And theta is going to be pi over 3. Those are the coordinates in polar. Okay. Again, I don't think this is complicated. You just got to pay attention to some details. Otherwise, it's not too bad. Now, let's do another example. In this example, we don't want to convert points, but let's say I'm given an equation. Let's say I have an equation. I want to convert the equation that is in Cartesian form, right? Convert it to polar form or polar equation. Because this is an equation. All right. So remember, the only relationships we know are x is r cosine theta, y r sine theta. So we've got to make everything work with those two formulas. I'm going to change x to r cosine theta, and I'm going to change y to r sine theta equal 1. And then do some basic algebra here. R times r, those two multiply to r squared, right? And then I have 2 sine theta cosine theta equals 1. And of course, we have the double angle identity, right? For sine 2 theta is 2 sine theta cosine theta. So I can write this as r squared sine 2 theta equal 1. Remember, our equation is going to be in the form r theta and there. So we converted a Cartesian equation into a polar equation. Let's do another example. What if I have, let's say, a horizontal line, y equal -3? What would the representation be in polar? Well, y is r sine theta. And there you go. R sine theta equal -3. That was too easy, wasn't it? Let's do another one. Suppose, and this last one. So let's say my Cartesian equation is x squared plus y squared is equal to x. Right? Now, we know x squared plus y squared is r squared. Correct? And again, for this one, we're going to go from rectangular equation to a polar equation. So x squared, y squared, I replace it by r squared, and x is r cosine theta. Okay. Now, here, because x squared plus y squared, remember that's the equation of a circle center at 0, 0, some radius. This cannot be 0. The sum cannot be 0, because if it's 0, you get 0 equals 0, the trivial case. Okay, so since r is not 0, and we know that, if I know r is not 0, I'm okay to divide by r, because I know I'm not dividing by 0, right? That makes it r is equal to cosine theta. And that's going to be the equation in polar form. Notice the equation in polar form is looks easier than the Cartesian counterpart. And there we have it. So here again, we're done with section 9.1, polar coordinates. Thank you for watching, everyone.